Hello, hello, hello. Today we're going to solve problem 2380. Time needed to rearrange a binary string. Um, please like, please subscribe, and please comment if you're real so that I know that somebody real is watching this video. Likely someone who is going through all the Leetcode problems or doing the contest because this is a very new problem. Um, this is definitely a very difficult problem. It took me quite a while to understand the linear time solution. So I'm hoping that this is an opportunity for you to kind of gain some understanding as well. I don't know. Okay, so you're given a binary string S. In 1 second, all occurrences of 0, 1 are simultaneously replaced with 1, 0. This process repeats until no occurrences of 0, 1 exist. Return the number of seconds needed to complete this process. Okay, so that's kind of what makes this problem strange because you can simultaneously replace any 0, 1 with 1, 0 within the set. So let's go ahead and just walk through this first example here. So in this example, we have S equal 0, 1, 1, 0, 1, 0, 1. And within this problem, right, we can simultaneously replace all 0, 1s with 1, 0. So if we just look through this string and we look at each example where we have a 0, 1, that's too small, that's too big. So we have 0, 1 here, 0, 1 here, 0, 1 here. After 1 second, right, so this is second equals 0, 1, 2, 3, 4, 5, 6, whatever. Right, we can swap all the 0, 1s with 1, 0s. So this becomes 1, 0, this becomes 1, 0, this becomes 1, 0, this stays the same. And then we can play that game again. This becomes 1, 0, this becomes 1, 0, everything else stays the same. And then here we have 0, 1 here. We swap that. And then finally, there's one more case of 0, 1. So after 4 seconds, right, it's the case where the system has no longer has 0, 1s. And to no longer have 0, 1s basically means that it's like sorted in this order where, you know, all the 1s are on the left and all the 0s are on the right. So again, the linear time complexity for this problem is difficult, and it's probably a hard, right? It's probably a hard to find the linear time, linear runtime time complexity for this particular problem. But the medium solution, which is an n squared solution, is pretty approachable, and we'll quickly just do that now, just so that you can see it. I'm guessing that you probably found that solution yourself, and you're here for the O of n time algorithm. But let's just go ahead and quickly do the n squared version, which is not unfeasible, right? Because there's only 1,000 characters at most. So an n squared algorithm would be 1,000 times 1,000, which is 10 cubed times 10 cubed, 10 to the 6, so only a million operations. So let's go ahead and do that quickly, just so you can see that such a solution exists. Well, if there's no 0, 1 in S, that means that there's no more swaps we have to do, right? So the whole system is sorted. Otherwise, we have to do another operation. So we'll do self dot, and then we'll take S and we'll replace all the cases of 0, 1 with 1, 0. And we'll just keep doing that until we process the whole string. So if 0, 1 not in, right? Because if it's not in there, then we'll have a solution. All right, so this is the n squared runtime algorithm. Why is it n squared? Well, we have to look through the whole string to replace 0, 1s with 1, 0, so that takes n time. And we might have to do that whole operation n times, right? We might have to keep swapping over and over and over again n times, so that's going to take n squared, right? So, for example, a case that would take n squared time is 0, 1, like this, right? Because after one operation, it'll be 1, 0, 0, 0, right? 1, 0, 1. Then the system has to look through the whole string again and swap all the cases of 1, 0. Then it has to do it again, right, and so on and so forth. You can see how this takes n squared time. So n squared time and then n space, right, because we allocate the stack, right? When we recursively run this, we keep going down the stack, and that could take n time. So this is a n squared time, n space complexity algorithm, but let's not spend too much more time. So in order to find the dynamic programming solution to this problem, you have to make 2 observations, okay? And these are 2 relatively difficult observations to make. It might require a hint in an interview, but let's just let's focus on the first observation, which is a little bit easier to understand. Is that observation number 1 is that any 1, right? Any 1 in the system will spend a second swapping with each 0 to its left. What I'm basically saying is that since a 0 and a 1, like 0 and 1s can be swapped simultaneously, right? But a 1 can only be swapped with 1 0 each second, right? So if we were going to look at a single 1, right? Like, let's look at this 1 here, right? This 1 is going to have to swap with this 0 and this 0, right? And it has to do each of those swaps. It's going to take a second to do each of those swaps, right? Because here it's, so let's color these 1s and 0s so we can kind of see how this is supposed to work, okay? So let's follow this 1 down its path. So it starts here, then it goes here, then it goes here, then it goes here. All right, so that's the path that this 1 takes down the system. And this red 1, 0, well, it swaps here and here. And this yellow 1 swaps here, then here, then here. So you'll notice that for each of these 0s that this 1 swaps with, right? Right, it swaps with the first 0 here, and it swaps with the second 0 here. Okay, and we'll play the same game again, but let's look at another one. Right, so this one had 2 0s to its left, and it took 2 seconds to swap with those 0s because it had to spend a single second swapping with each of those 0s individually. Okay, now let's look at this one here. So this one's going to definitely have to get all the way to the left, right? All the 1s need to be on the left, and all the 0s need to be on the right. So this 1 is going to have to swap with each 0 that's at its left to get, past it. It has to swap positions with it. So it's going to have to swap with this 0. It's going to have to swap with this 0. And it's going to have to swap with this 0, right? This green 1 is going to have to spend a second swapping with this 0, has to spend a second swapping with this 0, and has to spend a second swapping with this 0, right? Because, again, even though 0s and 1s can be swapped simultaneously, even though they can be swapped simultaneously, in 1 1 and 1 0 can only be swapped per second, meaning like this 1 can't swap with all these 0s at the same time. So it's going to have to spend a second swapping with this one, spend a second swapping with this one, spend a second swapping with this one. Okay, I'm beating a dead horse here. So let's follow the colors around. So green goes from here to here, then it swaps here, then it's here, and then it's here, down the system. This red 0 swaps instantly, and then it stays at the bottom for the remainder of the game. This yellow swaps here, then it swaps here, then it stays here. And this purple, right here, then it's here, it swaps here, here, and here. Right, so you notice again, it's the same situation. We have the 1 that needs to move and it has 3 0s to its left, so it spends 1 second swapping with this red one. It spends 1 second swapping with this yellow one. It spends 1 second swapping with this purple one, right? So 3 zeros to the left, 3 zeros it has to swap with. So that means that at any point, we know for sure it's going to take at least the number of zeros to the left of something to sort that system, right? When we look at this problem, we say, okay, it's going to take at least 3 seconds because there's 3 things to the left of this one, right? So if you had a problem like this, you'd say, okay, it's going to take at least 1, 2, 3, 4, 5 seconds because this one's going to have to swap with this one and then swap with this one and swap with this one and swap with this one and swap with this one. So that's kind of the first key observation, right? You know for sure that this system here, right, it's going to take at least 2 seconds because these 2 zeros need to be swapped with this one. And even we know it's going to take even longer than that because it's going to take at least 3 seconds because this one has to swap with this 0, and this 0. Okay. So then, well, you're looking at this problem, you're saying, well, the answer is 4. So sure, we know it's at least 3, but that's not even correct because there's an additional observation. There's an additional constraint that we need to consider. Well, I guess the second observation, which is a little bit more difficult than this first one, because this first one kind of intuitively makes sense, right? You have zeros to your left, you have to swap with those zeros, is that, let's go ahead and just, I guess the second observation is that for any system like this, so if we looked at this system individually, here, so the first 4 characters, it's going to take at least, if it takes S prime seconds for this system to finish, right? If it takes S prime seconds for this smaller system to finish, it's going to take at least S prime plus 1 seconds to sort this remaining system. Okay. Now that might not be the easiest observation to understand. The idea is, right, like, how do you know that if these things can swap simultaneously? How can you make any sort of assertion about when something can occur versus when something else can occur when it's the case that sorry, I was just thinking. When it's the case that, you know, how can you make that claim? How can you make the claim that it's going to take at least S plus 1 seconds if something before it takes S prime seconds? Well, if you follow this system through, right? I think a better example would be to look at, oh no, what was here? Shell 0. Okay, if you look at this system here, okay, we know the answer is 4, right? So what I'm going to claim is that whatever it takes this system, however long it takes to sort this system, it's going to take at least 1 second more to include this last digit. Well, why is that the case? Well, let's walk through. So if we were to sort this left system, when does this left system become sorted? If without respect to the last digit. So if we ignore this last digit in this system, so that's where this green is, when does it become sorted? Well, here there's a swap that has to occur. Here there's a swap that has to occur. Here's a swap that has to occur. So after 1, 2, 3 seconds, right? After 3 seconds, so S prime equals 3, right? This system becomes sorted, right? So this system here is sorted. Well, if that's the case, then how does that work in with the fact that this is, because it does take 1 second more, right? When this thing comes through, it takes an additional second for this system to become fully sorted? Well, I guess the observation is in order for a 1 here, right, that's waiting on a previous system to finish, the only way this 1 can move over to the left is if the blue system is sorted so it can provide it with the zeros it needs to swap with, right? If this system has a 1 here and zeros before it, or whatever the situation is, right? This 1 in its final position will be where? This 1's final position will be here. Right, when this system is done, so let's walk through this system. When this system is fully sorted, so let's just go through it. Right, so this green 1, if you walk it through its traversal, it ends up here. Right? Well, the only way it can end up here is if it swaps with the 3 zeros that are in its way, right? These 3 zeros are in this 1's way. So those are the zeros it needs to swap with in order to traverse this system. Right? So in order to do that, we need to swap the 0 with the 1, 0 with the 1, 0 with the 1, 0 with the 1. But in order for this 1 to move all the way to the left, all the zeros need to be provided to it from this system. So all the zeros in this system that it needs to swap with need to be on the right? Because this 1 needs to swap with all 4 of these zeros. So all these 4 zeros need to be next to it at some point so that it can be swapped with it. Well, that's only going to happen when this system is sorted, right? Because when this system becomes sorted, here, right, when we're talking with respect to the initial system, so if the initial system, if we painted them all red, right, this is the initial system here, and then here, so it's really just the blue parts. I don't know why I'm doing this. You notice that the red system is sorted here. So once the red system is sorted, it's definitely true that green has the ability to swap with all the zeros that are remaining, right? When the red system isn't sorted, like here, so let's just look at the red system. You'll notice that we can't, there's swaps that are occurring this green 1, right, is stuck here in this position, right, because it doesn't have a 0 to swap with because there's this 1 in the way, right? So this 1 can't swap until this blue system, where all the nodes are red, finishes sorting, right? Because it's confined by that system finishing before it can finish. So that's adding an additional bottleneck. So the 2 bottlenecks are the first bottleneck, where you have to swap with each of these zeros. It's going to take at least that long, but it could take longer if the system can't provide you with those zeros fast enough. So with that, let's go ahead and do this problem. So you start with the number of zeros that you have so far and the number of seconds it's going to take. you're going to look at each character in S. Now, if the character is a 0, all you have to do is just add to the number of zeros that you've seen. Else, if there are zeros already in the system, because this would mean that C is 1, then what? Well, it's a combination of both these factors, right? For this system here, how long is it going to take? Well, it could take 4 seconds because there's 4 zeros to the left. That's why we're collecting. Why did I do that? That's why we're collecting the number of zeros we've seen so far. When you see a 1, why do I keep doing that? Or it's going to be how long it takes to sort this system, and it's going to be a summation of both of those factors. So it's either going to take 1 second longer than the previous system took to finish, or the number of zeros that you see in the system. And then after that, you return seconds. Yep, like that. So what's the runtime of this algorithm? Well, it's O(n) time, and then the constant space. All right, thank you.